Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to be kind of an introductory video into the concept of inductance. So first of all, in order to understand inductance, there's a little bit of review we have to go through. First of all, magnetic flux. Anytime you have a magnetic field that's going through some sort of area cross-section here, you can calculate what's called a magnetic flux, which would be BA cosine theta. And the B cosine theta is the component of the magnetic field that's going through this cross-sectional area. You can calculate a flux for really any type of vector field, but the most common in physics 2 would be for electric flux and magnetic flux. Now, hopefully you've studied a little bit about Faraday's law of induction, which basically says this: anytime you change your magnetic flux, which you can do by changing either B or the A or the theta, you're going to induce an EMF or a voltage in that loop. And the magnitude of that EMF is going to equal the rate that the flux changes, change in flux over change in time. So it's necessary to understand Faraday's law to grasp induction. So now we're going to take a look at over here, this picture on the left here. We've got this simple circuit. And imagine when we close the switch here. Now, we're going to get a current in this loop that's going to be in this direction. And just to throw some imaginary numbers here, let's say that this EMF is 12 volts and this resistor is 6 ohms. So if you were to write a loop equation, it would read 12 volts minus IR equals 0, and it's pretty easy to solve that. You get a current of 2 amps. But here's the thing about that current. It does not get there truly instantaneously. If I were to just do a quick sketch of current against time, then I'll get there pretty fast, but not in a true time frame of 0. So that graph might look something like this here, where this is going to be our 2 amp current. Now, if they were in a lab setting or you're running some sort of physics experiment, typically by time you close the switch and then look at the meter, this time frame is passed and the meter will be reading 2 amps. But it's important to realize it does not get there at a time identically 0. There is some sort of small delta t right there. And that delta t is what we're going to be chatting about in this video. Now, remember that wires create magnetic fields around them. So the magnetic field, around this wire, it's circular. Kind of looks like this. This is the part that's coming at you. An important thing to realize is that within the plane of the loop itself, within this region, this stuff right here, the magnetic field is this way. And that's true pretty well everywhere over here. It's true if you grab the wire right here, thumb in the direction of the current. Again, the field's circular around it. That's going to put field lines, like so. If we grab the wire here, thumb in the direction of the current, that's going to give us field lines like so. No matter where you grab that loop, you're going to conclude that the magnetic field in the interior here is in the what I would call the minus k direction in a standard XYZ coordinate system. So another thing to realize is that magnetic field is a function of the current, right? Some function of I. And pretty well, if I pick any location within the interior here, like this point right here, the magnetic field at that location is going to be directly proportional, means equals some constant times the current. Now, that means that the magnetic flux, which is proportional to B, and B is proportional to I, therefore the magnetic flux through this entire surface is also directly proportional to I. Okay, now, one step further, that means changes in magnetic flux are also proportional to the current. Or I should say, actually, the changes in magnetic flux would be proportional to changes in B, which would be proportional to changes in I. Right. So that means we're going to get a voltage induced in this loop. Oops. And that voltage, by Faraday's law of induction, right, is time rate of change in magnetic flux. That means that this voltage is going to be proportional to the rate that the current is changing. So it's going to equal some constant times delta I over delta T. This proportionality constant is called the inductance. Right? It's a property of the loop, and it's created by the back EMF that's produced by this changing current. By the way, the polarity of the induced EMF by Faraday's law of induction is this way, opposing the battery, basically, if you will. Here's where that's coming from. So the current in the loop is producing magnetic fields that are in the minus K direction here. And remember, not Faraday's law, but the one that goes with it, Lenz's law, nature hates a change in flux. So the induced voltage will create a current that opposes the change in flux. That means that the current that would be created by this induced voltage would be such that it will create magnetic fields in this direction. Whoops, a little trouble with my screen there. So the induced magnetic fields will be this way, and that means the current would have to be this way. Doggone it. Again, the current created by this induced voltage. Now, overall, the net current is going to stay clockwise in this the entire time. The point of the polarity discussion was just realizing that basically the changing magnetic flux creates a voltage that fights the input voltage and holds the current down. Okay? So, again, the inductance basically comes from this. This current creates changes in flux through this area, which creates, by Faraday's law of induction, a back voltage. And that voltage, right, that is what we refer to as an induced EMF. And because the B is proportional to I, and that's true anywhere we are. Now, the magnetic fields are different all throughout this loop, but if I pick any spot, the magnetic field at that spot is directly proportional to the current. The flux is proportional to the field strength. Field strength is proportional to I. Therefore, the flux, the total flux through this cross-sectional area is directly proportional to the current. Therefore, changes in flux are proportional to changes in the current. And basically just divide both sides by time, and you get change in flux over change in time, which is an induced EMF, is a some other constant times delta I over delta T. So again, this property right here is what's called the inductance. I like to define it like this. Inductance is defined as rate, not a rate, resistance to changes in current. When a circuit has a very high inductance, it means it's very difficult to change the current. When it has a very low inductance, it means it's easy to change the current. So getting back to this original circuit, we imagine closing the circuit. That current would hit 2 amps pretty fast. That means it's got a low inductance. So graphically, this would look something like this. If I somehow created a loop that had more inductance to it, then this graph might look something like this. It'll take longer for the current to get to 2 amps. And if the loop had even more inductance, it would look something like this, meaning it'll take even longer to come up to 2 amps. Now, how do we create loops that have higher inductance? Whoops, screen's giving me a little trouble there. Well, inductance is coming from changes in magnetic flux. So you create circuits that have lots of changing magnetic flux. The most common example I can think of is a solenoid. So if you had, say, like an iron core, and you wrap your wire around it, oops, every time you go around the iron core, you're creating more magnetic flux for any given current. So circuits that look like this would have a high inductance. In fact, this symbol is typically the symbol for an inductor within a loop. Usually they don't draw the iron core. You just usually see, oops, something like this. So again, what is inductance? It's resistance to changes in current. What does it mean? If a circuit has a very high inductance, it means it's very difficult to change its current, and the current will take a long time to hit its steady state value. If the circuit has a very low inductance, the current will change very fast, hitting the steady state value pretty quickly. Units of inductance, by the way, if you just solve this for L, it's pretty easy to see that unit-wise, this comes out to voltage times time over current. So it has units of volt-second per amp. And 1 volt-second per amp has its own little pet name, like lots of things in physics. That's called 1 Henry. 1 volt-second per amp. So this is just meant to be kind of a conceptual video on inductance. Hope that this has helped with that. Have a great day.